The students from the Belmont High School Astronomy Club have entered a worldwide contest. There's one winner per country, and we're in it to win it for the United States. At Belmont High School Astronomy Club, guys, if you would just stand for a moment, turn around and wave to everybody. So this is and then in a moment, a little later, I'll introduce our president, who will be more formal in that introduction. And I want to introduce and give a special recognition to David Petriel. David, if you would stand. And it's really David's fault. And David has done an immense amount of research in bringing suggestions for stars and planets to the group. And through a process, we decided on a star and a planet. And he's just been a great mentor to the group in getting this program together. So thank you, David. Thank you. And one of the requirements for the program, for the contest, is having an onboard astronomer, scientist, and such. And so my good friend, Dr. Andrew Jordan, agreed very quickly, I didn't even have to talk you into it, to be our resident scientist for our group. And Dr. Jordan is a research scientist with U.N.H, and though he's an expert on exoplanets, which he's going to be talking about, he also is in charge of an instrument called the Lunar Reconnaissance Orbiter and the crater instrument specifically on it. So there's a spacecraft orbiting the moon, collecting data, and he works with that instrument and that spacecraft orbiting the moon. So the topic tonight is exoplanets, and Dr. Jordan is going to present about that. So a warm welcome, please, for Dr. Andrew Jordan.
Thanks. It's a full house. Yeah, it's excellent. I'll talk about this picture later on. I don't know. This mic isn't connected to the room, right? It's just for Zoom. And I am hoarse. Good combination. Is that a little better? Yeah? Okay. I'll explain this picture a little bit later on. It's really cool. It's one of the coolest ones I've seen. I don't study exoplanets personally. I have a little bit in the past. Most of my work is on the sun and how the sun affects our moon. So it's actually been fun preparing for this too. Just don't ask really hard questions. But I figured I'd start with a tour of our own solar system first before we start talking about other solar systems. So here is, roughly to scale, the 4 innermost planets. Some people kind of count the moon as sort of a pseudo-planet. The four rocky bodies that orbit pretty close to the sun. So you've got Mercury there in the top left, Venus, obviously Earth, then Mars, and there's the moon too as well for a sense of scale. Moon might be just a little big. And then if you shrink all those to the top left-hand corner, then you see the gas giants in the outer solar system: Jupiter, Saturn, Uranus, and Neptune. And Jupiter right now, I don't know if you noticed, did you see it on the way in? It's right next to the moon. It's pretty cool. And then you shrink down the gas giants, and then you have our sun. Our sun has about 99% of all the mass in the solar system, and everything else that's left over is in the planets, and then all these other objects. So these are the asteroids. We've discovered almost 2 million asteroids so far. As an undergrad for homework, we were supposed to discover asteroids. We had a cool little remote setup in New Mexico, and we would automate the telescope to take pictures of a certain area and then see if we could see any little dots moving across. And we would find asteroids. I found one, and then I lost it, so I don't get to name it. Probably somebody else has found it since then. If you find an asteroid, you get to name it, which is pretty cool. But as you can see, most of them orbit in that white region, which is just beyond the orbit of Mars, in between the orbit of Mars and Jupiter. That's the main asteroid belt. And then there's regions in green that you see on the left and the lower right-hand corner. Those are asteroids that are trapped in resonance on either side of Jupiter in its orbit. So they just go rotating along around the sun with Jupiter as well. And then there's some that are close to Earth. How many of you heard of the DART mission that just happened recently? Yeah, most of you have. That was a NASA mission that actually slammed into an asteroid to see if it could deflect its orbit a little bit, and it was quite successful, which is pretty cool. Oh, okay, and it does shine up on the other side, so I'll try to angle it down. I don't want to hit anybody in the face with this laser. So then here on the right, you see the moon, and then this is Ceres, which is the largest asteroid, which is also spherical, and then Vesta, which looks spherical here, but isn't actually. It's kind of oblong, potato-like. Actually, it probably looks more potato-like for you than for me. I'm looking at it from the side. And then this is another view of Vesta. So if you blow that up, you can see a range of asteroid sizes. And there are a whole lot that are about this small. And nobody knows how many asteroids there are, but it's probably, there are far more than the 2 million we've discovered. If you add all the asteroids up, it sounds like a lot of objects, but if you add it all up, it's only about 3% of the moon's mass. So there's not really that much mass in the asteroid belt. Don't worry, we're getting to exoplanets. We're almost there. So this is just a cartoon, not quite to scale. So there's the inner solar system, there's the sun. This green ring, that's the orbit of Saturn, then Uranus, then Neptune, this one that goes up out of the plane of the solar system. That's Pluto, and Pluto is part of a big group called the Kuiper Belt, or Kuiper Belt, depending on how you want to say it. And then you can see the paths of some of the spacecraft that have passed through this, the Voyagers, Pioneers 10 and 11, and then New Horizons is in the middle of the Kuiper Belt right now. And this is a region of, you can basically think of them as just comets. Probably some of the short period comets come from here. Pluto is like that. It's basically a big comet. If it got near the sun, it would have a big tail and it would look quite magnificent. And then there's a whole bunch of other objects out there. So there's Pluto with a number of its moons here. There's another objects. These are all artist's impressions, but they're to scale. And you can see down here is the Earth and the moon over on the left for a sense of the scale. There's Eris. I'm not even going to pronounce all of these because there's some strange names. That's a really bizarre looking object right there. And it has, I think it actually has a ring around it. And they all have, some of them have moons as well. So these are trans-Neptunian objects. The Kuiper Belt also has millions probably of objects. We don't know too many of them right now. I think we're up in the thousands or tens of thousands at this point. And so there's the Kuiper Belt, and that's just inside that little box here. And then we've never observed anything, but we know that comets are coming from here. There's the Oort cloud, which is about a light year across of probably very, well, obviously they're faint and they're distant, very cold comets. And occasionally some of them will be kicked by passing stars into our inner solar system. So there's this huge array of bodies just in our own solar system. We've got the star in the middle, and then we've got rocky planets, we have gas giants, we have little rocky pieces of planets, the asteroids that maybe never formed a planet, or maybe they were the remnant of a planet. We also have the comets, so those are icy instead of rocky. And the best idea is that they all formed out of a disk of gas and dust. And over the millennia, that disk gradually coalesced. In the core, we got the sun. And then where you see these gaps, that's where planets are forming. That's the real simple explanation. As you can see, this is an artist's conception of what the Milky Way galaxy looks like. And it's really hard to see. But our sun is right down here in the Orion spur of who knows what the arm is. I think it's the Sagittarius arm. That's our sun. There's about 100 billion stars in the galaxy. So you'd figure a few of them have to have planets. And if I were giving this talk maybe 20 years ago, we'd be like, yeah, hopefully a few of them have planets. We don't know. But now we know a little better about what it is. So what constellation is that? Orion. If you stay up really late, you get to see it. It's starting to come up a little bit higher. There's Orion's belt, and there's Orion's sword hanging down. And in the middle there is a patch of gas and dust called the Orion Nebula. This is a picture taken by the Hubble Space Telescope. And if you zoom in here, it shows you some other images, I believe also from Hubble. And it's kind of hard to see, especially for you in the back there. But there are a number of stars in this nebula that have little disks around them, disks of gas and dust. They're called protoplanetary disks. So proto just means before or early. So these are where planets might eventually start forming or are forming right now. It doesn't look like very much, kind of like tadpoles, baby frog solar systems. Doesn't quite look like this artist rendition. But fairly recently, a microwave radio wave receiver in Chile has taken this image right here. I'll actually show a picture of the telescope that did this. This is another protoplanetary disk, but now you're starting to see the rings. So all those gaps that you see in there are probably where planets are forming around the central star. And then for scale, I've got an ellipse showing about the approximate size of Neptune's orbit there. And it's not just some kind of one-off thing. These are all actual images of disks in which planets are forming, which is really cool. I don't even know if that's exhaustive or if there's other ones. The resolution of this telescope is pretty amazing. But not only can we image the disk, but we're actually starting to image planets as well. So this is Beta Pictoris B, and this is taken from the Very Large Telescope, which is also in South America, I believe. And you can see the images starting December of 2014, and they go for 4 years. Whoops, sorry, I almost hit somebody in the face with a laser. Down to here, and you can actually see the position of the planet. So this dark spot here is where the star is. The star is really, really bright. So they do a lot of image processing with the computer to get rid of the light from the star and leave just the faint light from the planet. I have no idea how they do this. It's pretty cool. And then you can actually see this planet is going around the star in some direction. Not everything is exactly side to be able to see the orbits perfectly. Here's another one in the constellation Centaurus. This is PDS 7dB, whatever that means. And this is actually a planet that's still in its disk. So that's the planet, the star is behind this black disk. And here you have the planetary disk or protoplanetary disk right here. It orbits its star every 120 years. And it's 20 times further away from its star than Earth is. So that AU is just an astronomical unit. That's how far away the sun is from the Earth. And it's about 3 times more massive than Jupiter. Here's another planet that's been imaged. It's that dot right there, that little dot right there. And that takes a whopping 228 years to go around its star. And it's pretty far out. It's a little bit bigger than Jupiter. I still can't get over the fact that they're taking pictures like this. Because when I was a kid, I grew up on just pictures of the Orion Nebula and the disks, and it's like, that's kind of cool, but not as anywhere near as cool as that. This is a movie right here of another star in Centaurus. So again, you've got the black disk in the middle, with that little yellow star is marking the location of the star. And so this is taken over a period of a number of years, and you can actually see it's about 2 years long. You can see the planet moving here. All this other stuff that you see in the background, that's just noise from the image processing. That's the planet right there. And it looks like it's about 15 AU away, which what in our solar system is 15 AU away from the sun? I think Jupiter is, help me out, Dave. That's
between Saturn is about 10.
Yeah.
And Uranus is about 20. So
Yep.
Between Saturn and Uranus.
You can see it's still pretty big. It's a lot harder to see really small planets that are Earth-sized because they're not going to be as bright. So there is selection bias. And then this is the one I started with, and you can actually see 1, 2 planets, that's another planet, and then there's a 4th planet right here. So you can actually see 4 planets going around this star. And all of them are much bigger than Jupiter. They're all about 10 times the size of Jupiter. MJ just means mass of Jupiter. And then their distances, they're all pretty far away. So you can see 16 AU and then all the way up to 70 AU. And they take anywhere from 50 to hundreds of years to go around their star. So some of these objects are really, really cold. Who knows what they look like? So there are a number of different ways to detect these objects. So the percentages that you see here are how many planets around other stars have actually been confirmed using these different methods. So that first one, transiting, you see a little picture of it there, is just the planet is a lot dimmer than the star. So if it passes in front of the star, you might not be able to image the planet. It's not going to look like that. But the brightness of the star will decrease slightly, or that's what it's going to look like. So it's a little partial stellar eclipse. And that is an excellent way for detecting planets. And I'll actually show you a spacecraft that has done that and has found thousands of planets using that method. So the bulk of planets are discovered using this. But to get that, you have to have the planet's orbit exactly lined up so that it's going to cross in front of the star. And about 20% of all the planets are found using the radial velocity method or the Doppler wobble method. And it's just that an object or two objects that are orbiting each other in space are going to cause a wobble. So a big, especially a gas giant, but you can measure smaller ones, is actually tugging on the star that it's orbiting. So the star doesn't just stay fixed in space, it's actually wobbling as the planet goes around it. And so you can measure how that affects the light. The light can be blue shifted or red shifted, that can be measured. And so you can discover planets using that method. And there's microlensing, which actually takes advantage of the fact that light bends as it passes through gravitational fields of objects. So there can be slight changes in brightnesses of distant stars that are beyond the star that you're wondering whether it has a planet or not. And as the planet moves in its orbit, it actually changes what the background stars are like. That's kind of crazy. That's only a few percent of planets are discovered that way. And then direct imaging, only about 1% have been discovered that way, which is still a number of planets. So here's a few of the different spacecraft, and one on the left, those are the Keck telescopes in Hawaii. So they're not up in space, but they're pretty close. It's a pretty tall mountain there in Mauna Kea. The one in the middle is the Kepler Space Telescope. That's responsible for the bulk of the planets that we've discovered so far. And this one on the right is called TESS. I'll mention it in a bit. So those disks of dust and gas that I showed you pictures of, that was imaged by the Atacama Large Millimeter Array in Chile. So also up on a high mountain, there's a bunch of radio telescopes all working as one. So they act like this enormous telescope out in pretty much a desert out there. It's clear almost every day of the year. And that's how they get such sharp images of those disks and the planets. Then, of course, the Hubble telescope has imaged some. I'm not going to show any pictures from that. It's still going strong after all these years. What is it up to? 30-something years now, right?
Yeah, 32.
It's amazing. Then here's the Kepler Space Telescope. The last time I checked, which was earlier this week, there's a little over 2,600 planets that have been confirmed, and I don't remember how many candidate planets. There are far more candidate planets than there are confirmed planets, just using this data set. And this was a spacecraft that launched in 2009 and operated for about 9 years. And it just stared at a single patch of sky the whole time. There were 500,000 stars that were being monitored. And it was just, scientists were using that just to look for little changes in brightness. And then once they found stars that changed in brightness and seemed like could have planets, then they revisit that to make sure the stars aren't some kind of a variable star where the star itself actually changes in brightness. And then once they've ruled out that the star is not changing in brightness and anything else, then they can confirm a planet. And now there's one that just launched in 2018, and it's still going on, the Transiting Exoplanet Survey Satellite, or TESS. There are thousands of candidate planets that have been discovered by this. I don't know how many of them have been confirmed. Apparently NASA didn't want to say how many it had. So that's doing something similar to Kepler, except it's looking at almost the entire sky, which is crazy. I'm not sure how many stars it's observing constantly. And then finally, the James Webb Space Telescope is also directly imaging planets, including the one that the Astronomy Club are going to try to name. So right now there's over 5,000 confirmed exoplanets, and you can see, so 1,800 of them are Neptune-like, so they're not that big, and they're probably fairly cold. 1,600 of them are gas giants, so bigger than Neptune, more like the size of Jupiter, or even quite a bit bigger, to the point where they're almost a star. Then there are about 1,600 super-Earths, so those can be up to, I think it's about 5 times the mass of the Earth. I'm not entirely sure. Then there's terrestrial ones, which are just a couple times the mass of the Earth, and all the way down to the mass of the Earth. And then there's 5 of them that are unknown. Nobody knows how big they are. And this is probably hard for you to see in the back. But what this is just a plot of all the different planets that have been discovered. The color that you see is what method was used to find it. So all the yellow ones are for the transiting method. All the blue ones are using the Doppler wobble, or the radial velocity. And I won't mention the other ones because those are the ones you can see the most easily. And then this is the orbital period. So how long it takes the planet to go around its star. So right here, it's 1 year. And then on the y-axis is how much mass the planet has. So if it's a small planet with very little mass and it has a short orbital period around its star, it's going to be down here. If it's a big planet, it'll be up here. And if it takes forever to go around its star, it'll be around here. So Earth is right here. And Jupiter is up there. And you can see there's a whole bunch of planets that are more massive than Jupiter. And there are a whole bunch of planets. Some of them are even smaller than Earth, which is crazy. That we can actually detect planets like that around other stars. And you think about how hard it is just to see Pluto. And then we're discovering all sorts of planets around other stars. And I'm actually going to skip this one. Probably some of you going, oh, don't skip it. And this shows, it's called a distribution of the different sizes of planets that are small and closer to Earth. And what scientists have found out is actually, so here's the size of the planet, and it goes from Earth. So Earth is 1, and then something that's 2 actually is 2 times bigger in terms of radius than the Earth, all the way up to 10 times bigger. And then how many planets are this big? So Earth is right about here. And there's a pocket of planets around other stars that seem to be about the size of Earth. And then there's another pocket of planets that are about twice as big as Earth. And then there's kind of this gap here in between. Is it real? Is it just because we don't have enough planets? I don't know. There's about 10 in each group, but we'll find out, hopefully. So the big ones are called super-Earths. And those aren't real pictures of the planets. They're just an artist concept to make it look cool. But being able to look into other solar systems with this level of detail is going to really help in understanding how do solar systems form and how does our solar system fit into that, into how it relates to other solar systems as well. It's sort of like when you're looking at one person, you don't know if that person, what characteristics of that person are unique to that person and what characteristics are just part of the person being a human. You kind of know what I'm saying? So most of us have 2 arms, but if you're just looking at a single person, you don't know, maybe some humans have 3 arms or 4 arms. You don't know until you get to see a whole bunch of humans. Well, it's the same way with a solar system. We had our one solar system, we developed a lot of theories about how the solar system formed, then we started looking at other ones and realized, oh, you can have a Jupiter-sized planet that takes a week to go around its star. We didn't expect that. And so then you have to revisit your ideas of how everything works. So this plot is of energy being received by the planet from its star. So we all get energy from the sun, which is really good because that's why we're alive. We get to eat plants that depend on the sun. And so this is about what Earth receives. This is energy that's less than what Earth receives, more than what Earth receives. And this green band shows kind of the Goldilocks zone, at least in our solar system, of getting just the right amount of energy from a star in order to be able to have liquid water on its surface. And then here's the temperature of the star. So the hotter the star, the higher up it is going to be here. So you see all these planets that are plotted here, and Earth is right there. We have a fairly warm star on this plot. And you can see there's already dozens of planets that we know of that are orbiting in what might be the habitable zone, which is really cool because we're getting to the point now where we can actually measure the atmospheres of stars. And once you start being able to measure the atmosphere, then you can maybe start being able to figure out, is there life? Are we going to be able to do that? I don't know. But this is a plot showing starlight, how much starlight there is as a function of time. So as time marches on, there's starlight, and then the planet goes in front of the star, and there's less light coming from the star. And then the planet moves away from the star, and then the light recovers. But not all the wavelengths of light are affected the same way, because the planet actually has an atmosphere, and some of the light gets through the atmosphere and some of the light doesn't. Just like at a sunset, when the sun's getting really low, you see more of the reds, because that can penetrate through the atmosphere, whereas the blue gets scattered away more easily. And this plot just shows exactly that. The red light is less blocked than some of the green light. And I believe this might be the same planet. They've actually measured, don't worry what all this is, just wavelengths of light, how much light is coming in at each wavelength, and they've actually detected carbon dioxide on this planet. It's a gas giant, it's pretty big. I don't remember what mass it is. But this is the first time that carbon dioxide has been detected on a planet outside our own solar system. So we're getting to the point now where we can actually tell quite a bit about the planet. Who knows, maybe we'll even be able to discover water vapor in the planet. I don't know, it's really exciting to see. And then the group is going to talk a little bit more about. This is the planet that they're going to try to name. And there's its companion star, and then here's the planet being imaged in 4 different colors of light, 4 different wavelengths. And it's in the constellation Centaurus. And it's a very slow orbiter too. It takes about 600 years to go all the way around. And then just to finish up, I'll mention some of the weirdest planets. These are all going to be cartoon pictures. They're not real pictures of the planets going around other stars. Kepler 16b is a planet, and it's that one right there. And it's actually orbiting 2 stars. So they kind of call it Tatooine, because you'd actually, if you lived on it, you would see suns set and suns rise, which is really cool. It does seem like it's probably a gas giant. It's not clear. And it's very far away from its stars, and its stars are pretty cool. Actually, no, it's not very far. It's closer to their stars than we are to our sun. But the stars are so cold that the surface of the planet is probably pretty cool. So it's not exactly like Tatooine. This one's pretty cool. This holds the record right now for the most number of planets that have been measured in its system. So there's 6 planets. All the ones we've measured are seem to be super Earths, which is pretty cool. So the smallest one is about 2 times the mass of the Earth, but some of them are really close to their star. They're orbiting only in 10 days. Can you imagine going around? A year takes 10 days. I'd get dizzy. This one right now is the most potentially Earth-like of the planets that we know of, Kepler 186f. So it was discovered with the Kepler Space Telescope. It takes about half a year to go around its star. It's about half the distance from its star that we are. And I believe it's in the Goldilocks zone because I think it's a fainter star. And it's F, so we don't use A because A is the star. Excuse me. B is the first planet detected around it, then C, then D, then E, then F. So that's B, C, D, E, F. That's 5 planets. And it's just a little bit bigger than Earth. So who knows what it looks like? It probably doesn't look quite like that. And if you're interested in learning more, exoplanets.nasa.gov, sorry I didn't make it any bigger. It's a great website. They have an up-to-date catalog of all the planets you ever want. You just enter in search terms, and you can find out the characteristics about them. And they also keep up to date with how many there are, which is really cool. So do we do questions now? All right, so if there's any questions. Yeah, way in the back. Oh boy, do I know this one? No, I don't, but if you write that down, If you write that down, you can look it up on the website. Kepler 186, remember that. Any other questions before my voice gives out completely? Yeah.
So what are these planets doing as they're orbiting? Are they growing? Are they shrinking? And what's happening with them?
Yeah. So if they were growing or shrinking, mostly growing, especially the ones that are in protoplanetary disks, we wouldn't be able to observe them growing because it would take far too long for us to be able to measure that. So maybe in 1,000 or so years, I'll get back to you and I can tell you if they've been growing. So for the most part, they're just going around. What else is going on? I don't know. There's all sorts of cool stuff that could be going on, especially around more active stars, younger stars. They could be having, well, they wouldn't be solar flares, they'd be stellar flares. That could be messing up the atmospheres of objects that are really close to the star. And so there could be some pretty cool things going on there as well. Just the interaction between the star and the planet. I don't know that we'd be able to see auroras on other planets, but we might be able to find evidence for things like that. So there's, that kind of thing could be going on. Yeah.
Is this still in the Milky Way galaxy?
Everything that I've shown here is still in the Milky Way galaxy. Yep. Everything else is too far away to be able to see at this point. Yeah.
Are you defining life in terms of how we live and the characteristics of what we need for life, or life that we have that's been imagined?
Yeah, that's a good question for an astrobiologist, which I am not. Last time I had biology was high school. There are different ways to approach it, and pretty much if you want to detect life, you kind of have to go with what we know. So it's carbon-based life forms, and we live in an oxygen, CO2 environment. So that's what you're going to be looking for out there. So do you look for signs of algae, photosynthesis, that kind of thing? That's what people are going to be looking at. And we've got plenty of satellite imagery of our own Earth. So we know what our Earth looks like from space compared to all the other planets. So it's kind of trying to tease all that apart. But yeah, that's a great question. Yeah.
Why are the size of some planets unknown?
Usually, it's just there hasn't been enough data. It's kind of hard to describe. If the orbit is tilted in a certain way and you only have a few data points showing how the planet has affected the star, it's not enough to be able to figure out the mass. And actually, one of the planets I was looking at, I was reading an article about it, it was very interesting, and they listed what the mass was, and it was pretty large. And then I went and looked at the most recent information about it, and the mass was a number of times smaller than it was before because they had been able to narrow it down. So some of the planets have very big error bars. We think the mass is this, but it could be quite a bit smaller or quite a bit bigger. I think there was another hand out here. Yeah. I'm kind of a planetary guy, but solar system planet guy. So I'm looking forward to that. It's already taken some pretty cool pictures of, was it Uranus or Neptune? And I can't even remember, and Jupiter. So I'm looking forward to that kind of imaging. And then imaging exoplanets is really cool. And we've already used the James Webb to find carbon dioxide on another planet. So hopefully more atmospheric studies, because that to me, that's pretty exciting. Yeah.
You said earlier about deflecting meteor. How big was the
Oh, how big was the asteroid that was hit by DART? It was pretty tiny, but I don't remember how big it was. Was it a few hundred meters across? It was pretty tiny. But if you hit them early enough, you just have to tweak the orbit a little bit.
Have you done that before?
No, this is the first time we've done it. Yeah. Yeah, slow and steady wins the race with this.
The last call for questions?
Yeah.
How far from us are a lot of these systems, these exosystems?
You know what would be really cool is to go back to that Milky Way map and just have them all plotted on there. They're over a range of distances. I can't remember. I don't think there's a whole lot more than, I'll say, 1,000 light years away or so. Because the further away it gets, the harder it is to see everything. But there are some pretty bright stars. So I think it just covers a range. That's my hand wavy, wishy-washy, go look it up for yourself answer. Yeah, I see one hand way back there. The biggest asteroid? This will be the last one. It is. There we go. So this one right here, it's called Ceres. And I think it's right on the edge of what you can see with the naked eye, right? Is it magnitude 6-ish?
Yes.
Have you seen it?
No.
Oh,
Uranus is also, I haven't seen that one yet either. It's 5.8.
yeah.
Are you serious about that?
Yeah.
No. They're catching on. How about a round of applause? And we're, again, very thankful in our club to have Dr. Jordan as part of our team on our exoplanet quest for naming this star and planet combination. And a lot of what he talked about in terms of the different ways of finding things are going to manifest themselves in our planetarium show. You're really going to enjoy the planetarium show in 8K. It's just really crazy. So you probably have had experience trying to plug in like a USB, right? It's always the third way that works. It doesn't work this way. It works this way. So it's detecting my device, which is good. Which is good. But it's not fast enough. Do I need to do something with my TV remote? Yes, no?
If you just unplug the HDMI and plug the laptop.
All right, we'll leave that. Yay. Aw. Why did it go away? Yay. All right, looks like we might be in business here. So awesome. So let me just warn you guys, I'll flip through the slides, just tell me when you need the next slide, and we'll do that. Planetarium show, you're really gonna love it. But next on our show, we have the Belmont High School Astronomy Club, and Tyler Flanagan is president of the club. And Tyler, if you want to come on up here, I'll let you introduce the rest of the gang from the club, and we'll continue. Yeah.
So we're the
You can watch out for this, it's gonna kill you.
Belmont Astronomy Club.
You gotta speak up, but here at the back.
This is the main officers here. I'm Tyler. This is Reese, Andrew, Vice President, and Zoe. And then we have our other members here. We have Aaron.
Why don't you come on up, just so we can see you. No, you can stay over there.
Okay, fit over here. Do you want to introduce yourself?
I'm Aaron.
Hey guys. Jenny.
Come on up, just, you
come
can
on
start
up.
filling up the other
Stand
side
up
of the
here.
screen. Stay on that side, yeah, and then we'll balance.
Rachel. Ari. Brendan. And Piper. And then this is the astronomy club.
Look away.
My bad.
All right, round of applause.
So today, along with Dr. Jordan and David Petriel, yeah, as our club advisor, Mr. McDonald here, we're presenting our exoplanet naming for 2022. This is against the whole U.S. basically. We're really trying to get it here. So yeah, we're just trying to gain your support for these names. Hopefully you like them, and we're trying to win.
They can sit down if they want to.
Yes. Who's on this side?
Yeah, you guys can stay.
So, our planet, our star and the planet. The star is in the constellation Centaurus. Also, I'm really bad at public speaking, so like, bear with me. The mass of our planet, HIP 65426, is about 3,000 times the mass of the Earth, but it's only like 17 times larger. It's like a really condensed gas giant, which is great. It's really far away from its star, and it's really large. And the star is about 14 million years old, which is, it sounds old to us, but like there's older stars. It's relatively young. And like usually stars have like a disk of dust and stuff, and that's where like the planets form and stuff. But that's like not a thing with this one. And it's the first exoplanet that's been like directly observed and imaged by the James Webb Space Telescope. There's not really we don't really have like a solid explanation, like a confirmed explanation as far as like why there's no gas disk or why the star spins so fast. But we do have a theory. And the theory is that another planet was formed along with the planet that we know of here. And that planet, one way or another, got knocked into this planet, our planet that we know of, and knocked it like way far out, which would be why it's really far out. And also, yeah, and also when that happened, the other planet really got knocked into the star, which is why it's spinning so fast, and it kind of essentially stops.
Yeah, very good.
So our
Thank
first.
you, Zoe.
So our first idea for naming was a chimera.
You guys just gotta speak up so I can put it back.
So our first idea was naming it after chimera, which is chimera, which is it was a Greek, it's from Greek mythology, and it's usually like a humanoid animal with just a bunch of different animal parts and human parts. And we chose chimera for being in the Centaur system because a centaur is like a bull and a horse, something. I don't know what it is, but yeah. So this is a minotaur. our first name was for the star, the Minotaur. The Minotaur is obviously big and very ferocious, and the star spins like 150 times faster than the speed of our star, so spinning very fast. And we just thought of the size and how we theorized the star consumed another planet. How like centaurs were usually fed people for like sacrifices and stuff, or minotaurs. But yeah. And the name for the planet was supposed to be Launsu, which is another chimera, and it's a bull with a head and wings. They were usually statues on the outside of gates, like how the planet is like so far out on the solar system that's in. And yeah, we just picked this one to kind of fit the idea of how far it was out and being a chimera. This is okay. This is our second scheme. Sorry, this is the second naming scheme we have. It's the United Worlds of Babe. It's the Blue Ox and Paul Bunyan, and yeah,
So we came up with this other idea, and it's based off the North American folk tale of Paul Bunyan, and a lot of the idea came from how just big the star and the planet are in comparison to a lot of other stars, and Paul Bunyan and his Blue Ox babe are very large in the folk tales. So that was really where we came up with the idea, and also the folk tales are very young compared to other legends and myths from history, and the system is relatively young in comparison to a lot of other systems in our universe and galaxy. And so Babe is blue, the Babe Blue Ox, and our star is a blue sequence or blue main sequence star. And so, it kind of fits. The star is also way bigger than the planet. And, Babe is bigger in comparison to Paul Bunyan. Way bigger. And so, we thought, ox can, name the star after the ox because the ox is blue. And then, you have Paul Bunyan. He's also big. The other main reason why we decided to name the planet like this. And the pair fits with the star and the planet, which is the only planet we know of, if I'm correct, in the system. So, the pair, which, fits the super Jupiter that the planet is. Yeah, you can skip it. And, for if there are other planets, when that comes, you have various other American folktale and lore, such as, I can't take this bill. Take this bell. The greatest cowboy to ever live. You have Joe, Margaret, Pittsburgh's Man of Steel, and Alfred Bulltop Storm, a 30-foot tall sea captain, along with many other American folktales and lore you find.
We voted as a club on which one we like the most. The winner is. Well, before we do that, we want to show you the thinking process for our final choice. They're voting in a club as well as for our friends, and with a winner. And the winner is, okay. The winner is United Worlds of Babe.
Just want to find out as they go through this, that we had United Worlds of Babe and Chimera theme that Andrew, Dr. Gordon, and Dave Petriel have put together the slides for the students to put together, and they did a lot of research themselves and put it together. So kind of an eclectic teamwork from the students, Dave Petriel and Dr. Gordon, and getting these slides together. So just want to credit to students, credit to students. Okay, continue.
We already done this, I think.
That's where it is.
Yeah, so this is our actual our star HIP 65426. The very
It's a
star.
great password, by the way.
Yeah. At the very star of Centaurus is.
It won't come March.
Very star center of Centaurus, I guess, is where the star resides. It can be found, I guess, here, or the stellar coordinates there. I don't know. It can be found at the stellar coordinates here. I don't know really what those mean, but yeah.
The RA is right ascension, and that kind of corresponds to latitude lines. And PC is declination, and that corresponds to lines of latitude. And longitude is the RA.
So a little information about the star is it's the most massive star in the competition, over 2 times the mass of the sun. The second hottest star in the competition, 9,000, I don't know what, Kelvin. Its stellar class is A2V, and it's a blue main sequence. The planet, HIP 65426b, most massive planet in the competition, 3,000 times the size of Earth, and 9 to 10 times the size of Jupiter. It is 92 AUs away from its star, and like we said before, it's believed to be pretty young compared to other star systems in our solar system. And the first exoplanet directly to be observed by the James Webb Space Telescope. And picking a name, we one theme stuck out. Size of these were just huge, and we thought, you know, something with a name that fits something with a big size would be good for it. And then we considered our own country, because I mean, naming it from something from a different country would kind of defeat the purpose of us winning it for our country. You want to do the next?
So this is a little lore for Paul Bunyan. He was born. It's not real, by the way. It's not real. Yeah, he was born in Maine, Bangor, Maine. 5 fully grown storks working overtime to bring him to his parents. That's how he was born. He moved out west after Paul's turning in his sleep, causing massive waves to rock the coast. Grew to 63 axe handles high, which is about 189 feet or 57 meters. He cut an acre of lumber in one swing, logged the Dakota solo, and according to legend, created 10,000 lakes in Minnesota with just his footsteps. And this is his off's babe. The winter of blue snow. So cold that geese flew backwards. Words froze solid before they could be heard. The snow itself turned blue when he was around, and Paul found a baby ox in the snow, blew from the cold, and brought it with him. It thawed out, but remained blue, and he adopted it, naming it Babe. This is both of them combined now. Babe grew with Paul Bunyan, growing even larger than he is. He's 47 axe handles, and a plug of tobacco between his eyes, which is 141 feet. He ate 30 bales of hay, wire, and all for breakfast, and a ton of grain for lunch. Paul and Babe grew inseparable, and Paul chopped the lumber, Babe hauled it without complaint. So these are some things that he's done. He made the Great Lakes with just stepping, and that's just water for Babe. The Grand Canyon, where he dragged his axe around Arizona, cleared the Great Plains and logged the Dakota solo. When Babe died, he buried him, and that became the Black Hills. And then he finally retired to Alaska at the last frontier. What more appropriate names for such giant worlds as these giant legends? Therefore, we'd like to name the world HIP 65426b Bunyan after this legendary lumberjack, and his companion, the star, HIP 65426 after Babe, his trusty big blue ox.
So if we find any more planets in this system here, we have a few more names from American folktale to name them. Pecos, from Pecos and Bill, the greatest cowboy that ever lived. Magarac, Pittsburgh Man of Steel, Stormalong, a 30-foot tall sea captain, and there are a lot more, including John Henry, Cassie Jones, and any more that we decide to think of anymore. And these are, under 100 years old, so they're appropriate for folklore because the system is so young. And that's all we have.
That's it.
Questions? At the back.
I have a question about the letter naming of so the planet closest to the star is
Correct.
Yep.
but this is so far out, it's likely that one might be found closer to the sun, so that would be
I don't think they changed the names.
I can just give it.
It's in order of discovery.
Yeah. In order to discover, so they're not going to change the name.
So, but that could be confusing long term, right? Because in some sources, it goes in order from the sun, and then in others, it goes in order from the country.
Right. So the publication people have to make that clear. So when they write in textbooks, you want a good textbook publisher that makes it clear so kids can understand it. All right. Other questions? Right here?
When we find out if you won.
The deadline is the contest is being, they give out the names, the winners, I believe, on March 23rd of next year.
So,
March
a while.
23rd, 2023.
About 4 months, 5 months.
So 3/23/23. And we are in it to win it for the USA. What do you think? Do you think this is a winning? Other questions at the back?
How many people are taking part in this competition?
You
That's a
mean
good
in our
question.
school?
No, it's a total.
You have an idea, David?
I've seen a couple of other teams, but surprisingly few. But I can neither say one way or the other at this point. We'll have to see. I will be frank and honest. It is tough. Given what this country's relationship with space is just like, and how frankly fascinated it seems that everyone is with it. It's like, I'm not gonna deny, it's gonna be a stiff competition.
And we have, again, I think I mentioned that it's one winner per country. So we're in it for the USA at the back.
So, in this competition, you guys do this presentation, and when does that happen?
This is the presentation
Yeah.
you're here for.
Yep.
Right.
I think
Yeah,
she's
this is the only one.
When it's done, is this now been recorded and you're submitting this, or is this?
Yes.
Yeah.
Yep.
But this is not the end of it, though. You guys know what else is involved in this?
We
No.
also have to
What is it?
write a 300-word essay to explain our naming and our rationale behind it.
300-word essay to
Then-
name our naming rationale.
Do we send that to NASA? Yeah, we send that to NASA, and then they, get to pick the winner. Yeah, I just realized that.
And we have to put together a 3-minute video, of which this will be part of. And we need a resident astronomer scientist. Dr. Jordan, thank you very much. Any other parts, David, that I missed?
The only other thing, like I said, is we had to hold this event, educating the public about exoplanets and record that, report about, the event and how everything went, so, have fun.
Yeah, your support
Did
helps.
you feel educated? Yeah.
Sprint out of here.
The judges are the International Astronomical Union themselves, along with the discoveries of the world. And so this is going, straight to the IAU.
And that's spelled just like it sounds, IAU. International Astronomical Union.
How will we know where you are in the process
Oh.
at different points?
Well, the
Email subscription.
deadline to get in has been extended to December 11th. So it's like we're in the home stretch right now. soon as we, like I said, I don't think the public at least will hear, much about us until we discover whether we won or not.
So stay tuned, that's kind of a little bit of an unknown on our end. We'll make our submission certainly by the deadline in December 11th. And then the winner is 3/23/23.
You think it'll be in the newspaper?
And
Like,
hopefully we'll know. What's that?
you think it'll be in the newspaper like it was today?
Oh, I'm
The
sure.
news will most likely
Yeah,
cover
you
it.
check the newspaper
Oh,
too.
I'm sure.
It might be in
If
there.
we win, front page.
I actually don't.
What has been the hardest part of this whole process for you guys?
I think meeting, like getting everybody
Yeah.
to kind of conjoin together and with our club. I mean, it's hard to get high schoolers to come after school to talk about this type of stuff. So it's I mean, we've done it, so it's done, I guess. But yeah, that was probably the hardest
But
part.
these are the main kids here who came today. It really helped.
Actually, these are the New Hampshire kids.
yeah. These are the main New Hampshire kids.
I'd like to shout out Landon. Should we?
Will part of the process or at some point, can there be something sent to the planetarium here to let us who are interested know
If we win, yeah.
No, I think.
what's
Yeah,
happening?
we can keep you informed of
Yeah,
what
we
know.
can let them know what we know, and then they'll portray it to you guys.
Yep.
Yeah.
I appreciate you, we appreciate, all your interest, and this is a great crowd showing interest in this. Yes?
He had a question real quick.
Go, right, go.
Yeah, so, you said your planet was 92 or 93 AU from the sun.
Yeah.
In relation to our own solar system, how far is that?
So an AU is a distance from Earth to the sun. So it'd be about 93 times
So as
our
far as
Earth to the sun.
Twice as far as Pluto is.
yeah, twice as far as Pluto is.
Visualize that distance. I know it would graphically visualize that distance. I just would.
Yeah, twice as far as Pluto.
Oh, okay.
Yeah.
Yep.
Great.
Did you have one back there in the back? No. Okay.
Can I add on, so
Oh.
there's a website on, I believe it's on NASA's website, Discovering Exoplanets. If you look up the name of this planet, you'll find, it has a visual of like how far away things are. The distance didn't click for me until I really like zoomed out and saw just how far away it was. So, yeah.
Did you have a question in the back?
Yeah, do you know anything about the composition of the planet at all?
Like the like the environment of it.
Yeah,
Like
I didn't see anything about the
Well, it's
atmosphere.
so far away. It's probably ice. I mean,
yeah,
it's
From what I was able to pick up, there's a lot of dust.
Yeah.
But not much beyond that. Like I said, it's like a lot of dust, but it's also massive, so it could ironically also be generating some heat.
And this is, as was pointed out, the first exoplanet imaged by the James Webb Space Telescope. And, I mean, this thing has just really started in earnest, like in June, July. Hasn't even been really in full operation for a year yet. And I think they're going to learn how to tweak this and that, and I think we'll be able to learn more about these things with the James Webb Space Telescope. So I think this, the last chapter has not been written on this star and planet.
yeah, especially if our planet wins, we'll get to know a lot more.
We
Hopefully
will.
it'll be a focus.
We'll go on tour.
Yeah.
go on. Sit in your own planet and leave.
Well, we're gonna
That's a way
take
of
like
raise
a
money.
10-minute
What? It's a way
break
to
so
raise
you
money.
can get some water, so you can use the restrooms, and then in about 10 minutes, make your way to the planetarium theater, and you're gonna love the planetarium show Beyond the Solar System, which is about finding these things. And if you wanna pop outside and look through some telescopes, that's fine, but come back in for the planetarium presentation about 8:15. How about a round of applause for our students? Thank you. 10 minutes at the Planetarium Theater entrance.
No.
Awesome, you missed it. So you did what?
I was
I'm scared. You're not wanting to speak. You wanted to speak.
That was
Nice job,
pretty
Rick.
nerve-wracking, I'm not gonna lie to you.
If I had been out here, I would have done better than all y'all, okay?
Yeah, I know you would.
I